So today we're going to be covering Chapter 5, Stereoisomerism. This is Chemistry 3053. We're going to cover this chapter in 3 days. The first part will be stereoisomers and their nomenclature. The second part will be on optical activity and some concepts related to that. The third part will be more detailed concepts about specific topics of stereoisomers. So the first one will be sections 1 through 3, and then sections 4 through 6, and then sections 7 through 11. So let's go ahead and start. So we're covering here, this is a little review of isomers. Remember, we had constitutional isomers. These are the ones that have the same molecular formula but different constitution. In other words, the atoms are connected in a different order, but they'll have the same molecular formula. Here with stereoisomers, they have the same connectivity, the same molecular formula, the same connectivity, but the groups or atoms will point in different directions, so they'll have a different spatial arrangement. So those are the two different kinds of isomers generally, and you're going to see a lot more topics under stereoisomers in just a moment. So here's an example. You've already seen this to some extent. We've gone over this previously. So these are two different stereoisomers. Notice the difference is up here, the two methyl groups on this cyclohexane are on the same side of the molecule, so those are called cis. Here, the two methyl groups are on opposite sides of the molecule, so these are trans. So cis means on the same side of the ring or of the double bond. You'll see it pertaining to a double bond later in this chapter. And trans means across. So it means on opposite sides of the ring or the double bond. So the word cis in italics, followed by a dash, will precede the name of the molecule in the nomenclature. Or if it's trans, the word trans will and again, it's italicized, followed by a dash, and that will precede the name of the molecule to designate this stereoisomer. These are totally different. They'll have different melting points, boiling points, different spectra. They're easily differentiated. And so here you can see the cis and trans concept applied to carbon-carbon double bonds. So this is applied to alkenes, and you see the same thing. You see the two methyl groups on the same side of the carbon-carbon double bond. This is cis 2-butene. Again, it's in italics, followed by a dash preceding the name of the molecule. This is 2-butene because 1, 2, 3, 4. The double bond starts at the 2 position in butene. Here, 1, 2, 3, 4. This is 2-butene because the double bond starts at the 2 position. And this is trans, again, trans in italics, followed by a dash to indicate the two methyl groups are on opposite sides of the ring. These are not interconvertible the way you saw that conformers were interconvertible. Remember, conformational structures, gauche, anti-eclipsed, staggered, those are interconvertible without breaking any bonds. There you just have rotation about a carbon-carbon single bond in order to interconvert those different conformers. These are actual isomers. And here, in order to interconvert, to switch from one isomer to another, you would have to break this pi bond. So these are not interconvertible, not easily. You have to heat this to a pretty high temperature, say 400 degrees centigrade, in order to accomplish that. And you can see the pi bond here is represented by the overlap of the p orbitals above and below the plane of the molecule. So some of that is review. So here, just to go over this, here is a little exercise. Identify the following pairs as either constitutional isomers, stereoisomers, or identical structures. Here, remember, you can interconvert the equatorial position to the axial position by simply doing a ring flip. So these are two different conformers of the same molecule, because all it takes is rotation about carbon-carbon single bonds. However, here you have hydroxyls, the alcohol functionalities. These are on the same side of the ring. You have OH coming up, and here OH is coming up with a hydrogen going down. So these are on the same side of the ring. In this molecule, a hydroxyl group is going up, and a hydroxyl group is going down. So this one is going to be cis, this one is trans. These are different stereoisomers. In order to interconvert here, you would have to actually break a carbon-oxygen bond. These are constitutional isomers. They have the same molecular formula, but a different connectivity. These molecules are identical. You can see that one of the ends of the carbon-carbon double bond has one methyl. Here it has one methyl. Over here, the other end of the carbon-carbon double bond has two methyl groups. This one has two methyl groups. These two are identical. Here, you see that this again is an alkene. This is 2-pentene. And you can see that the two alkyl groups on the ends of the carbon-carbon double bond are on opposite sides of the carbon-carbon double bond. Here they are on the same side of the carbon-carbon double bond. And so these are trans and cis. And so these will be stereoisomers. Just like those, cis and trans are stereoisomers. Now, once again, we're going to identify these, just go through this little exercise, as these being, these stereoisomers being cis, trans, or neither. Here you can see that this alkene has the alkyl groups on the same side of the double bond, and so this is a cis stereoisomer. Here you can, we just saw this, this has the alcohol functionality and this alcohol functioning on the same side of the ring. So this is a cis stereoisomer. Here you see that the two alkyl groups are on opposite sides of the carbon-carbon double bond. So this is a trans stereoisomer. Here the groups are on opposite sides of the ring. This is trans, and here this is neither, because these two groups are the same, and so they're equivalent. So this is this methyl group is cis to one methyl group and trans to the other methyl group. So there's no isomers here in this one. So this one would be categorized as neither. This one does not have another isomer, a stereoisomer. Now, more about stereoisomers. Cis-trans isomerism is only one type. There are other types of stereoisomers. In those molecules, a great example is of when you have chiral molecules. A chiral molecule is asymmetric. That means it does not have symmetry. If it has symmetry, it will not be chiral. So one type of a chirality is when you have mirror images. Those would be enantiomers, just like it's said to be a handedness, and that's another way to describe it, because the same way that your two hands are identical, you might think of them as identical, they're really not. Your left hand will not fit in your right glove, and your right hand will not fit in your left glove. So these are, your hands are mirror images. And so there's a handedness in molecules also, in some molecules. And those molecules that have mirror images are said to be chiral molecules. And just like your hands might be said to be mirror images of each other, you could think of them as being chiral. Okay, so they're, in order to be chiral, they are not superimposable on their mirror images. So your right hand is not superimposable on your left hand, just like I said. Your right hand won't go on your left glove, etc. So these are molecules. I suggest that you build these. This is a set of molecules that demonstrates chirality. You can think of a plane of symmetry being here. So this molecule is a reflection of that molecule. This is a mirror image of that molecule. And so these two molecules are chiral. This molecule and that molecule taken together are enantiomers, okay, mirror images of each other. They are a pair of enantiomers. So this carbon is said to be a chiral carbon, or a center of chirality, or a chiral center. There's different ways to describe these, different names that can be used to refer to this. And so these two drawings are the same as these two drawings, except these are sort of representations of your molecular models. And here these are just simple drawings, simple bond line notation. And here you can see, so this would be the hydrogen. And here you can see this is blue, just like that. So the two hydrogens are pointing toward each other, just like here, they're pointing toward each other. And then you can see the green methyl groups coming out at you. And then you see the white ones going back. That would be ethyl going back, and the hydroxyl group going up. And so hopefully you can see the relationship between these pictures of your molecular models and these bond line drawings with the mirror plane in between. So this is, again, a mirror image of that molecule. You have to be able to sort of envision this. Hopefully you can just look at it and automatically see this. If not, then you'll need to study these until you can, and perhaps make molecular structures and play with these and turn them around so that you can actually convince yourself that this molecule is not superimposable on that molecule. If you have the red group going up and you move this over to try to superimpose it, you can see that the blue will not superimpose on the white and green. Here the white and green will not superimpose on the blue. So they're not the same molecule. They are indeed mirror images. So this happens when you have a tetrahedral center that has 4 different groups. Let's go back and look at that. So you can see this carbon has 4 different groups. It's an sp3 hybridized carbon. If you have sp2 or sp, you will not have chirality at that carbon. So it has to be an sp3 hybridized carbon, tetrahedral, and it needs to have 4 different groups. It needs to be bonded to 4 different groups. So here that's represented. This carbon does indeed have 1, 2, 3, and CH is going back. And remember, we don't always draw in the CH. You'll have to be able to just look at it and know. And so this has 1, 2, 3, and then the CH going back, 4 different groups. This one has 1, 2, 3, and then the CH going back, 4 different groups. And this carbon is chiral because it has 1, 2, 3, and the CH going back. So it has 4 different groups attached to it. So each one is a chiral molecule. Each one of these is a chiral center. Each one of those is a center of chirality. It means the same thing. Or a chirality center or a chiral center. They all mean the same thing. So if you see different phrases that I just mentioned, don't get confused. They all mean the same thing. So, how many chirality centers or centers of chirality here? You can see there is 1. This is CH2. That's not going to have 4 different groups. That won't have 4 different groups, or this one, or this one, or this one. This is the only carbon that has that's sp3 hybridized. But look, you can see it has a CH and a CO. But look at these 2 groups. These 2 groups are the same because this molecule has a plane of symmetry and passing through this this carbon and that carbon. It has a plane of symmetry, and any molecule that has a plane of symmetry is not chiral. So this molecule is not chiral. It does not have a chiral center or a chiral carbon because these 2 groups are the same. Okay. Here, let's look at this molecule. You can see that it has a carbon atom that has 2, 1 hydroxyl group and a CH group, and then this group and that group, and the group going around the ring this way is not the same as the group going around the ring that way. So this has a chiral carbon. This, similarly, is a chiral carbon, or it has a chiral center there, or a chiral center here, or a center of chirality. I'm not going to keep giving all the different names because it's time-consuming. Here, you can see this carbon has 1, 2, 3 different carbons attached to it, and so and CH coming out at you. So that's 4 different groups attached here to this carbon. So this carbon is a chiral carbon. Over here, you can see, and here similarly, this carbon has 1, 2, 3, and then the CH bond. This has 4 different groups. That's a chiral center. This one has 1, 2, 3, and CH, 4 different groups. 1, 2, 3, and CH, 4 different groups. This one is not chiral because it's sp2 hybridized. Okay, so it has 2 bonds to that carbon. This is not a chiral carbon. Over here, this is not a chiral carbon because it has 2 methyls. Okay, so remember, it has to have 4 different groups or 4 different bonds. You can think of it that way. So this has 2 chiral centers and this has 2 chiral centers. Some stereoisomers are also special because they have a mirror image, just like this one has a mirror image. If it has a mirror image, it is chiral. It must be chiral in order for it to have a mirror image, but not all chiral carbons. Just because a molecule has a chiral carbon or more than 1 chiral carbon does not mean that it will have a mirror image. So that is a different molecule. Okay, we'll see more of those in a minute. But remember, this has a CH, so this is a chiral compound, and it has its mirror image. These two are mirror images of each other. They form a pair of enantiomers. This is one enantiomer. That is the other enantiomer. This is a pair of enantiomers. Okay, just like your left and right hand are enantiomers and form a pair. Okay, so their mirror images are enantiomers. So an easier way to draw the other enantiomer, if you have this, is just to simply put the CH coming out at you and the CCl going back, and you've drawn the enantiomer of this compound. So, and the same thing here. Now, so this is not a chiral compound. Why not? Because these two methyl groups are equivalent. You have to have 4 different groups on a carbon in order for that carbon to be chiral. If you don't have a chiral carbon, you don't have a chiral molecule. And you cannot have enantiomers. Okay, these are different, totally different compounds. They'll have different names. However, enantiomers are very special compounds in that they are very difficult to distinguish between each other. They'll have the same boiling point, melting point, the same reactivity towards most molecules, the same vapor pressure. It's very, very difficult to distinguish between these, and we'll talk about later on in this chapter, we'll talk about the very few ways that these compounds can be distinguished, and it's even harder if you have a mixture of enantiomers. It's very difficult to separate them. Although it can be done, it is quite difficult. And we'll look at 3 different ways. So, the Kohn-Ingold-Prelog system is used to name these chiral compounds. Okay? And sometimes this is abbreviated as CIP. So, the CIP system is used to name these chiral compounds, these enantiomers. So let's look at one of these. R or S is assigned to a chiral center using a stepwise procedure. So here are the actual steps. Okay, so first you have to prioritize the 4 groups attached to the chirality center. So let's go back here and prioritize these 4 groups. So let's use this one, not the one on the right. These are going to be opposite. If this one is R, that one will be S. If this one is S, that one will be R, okay? And it will be named according to this chiral carbon. The attachments at this chiral carbon will be what will determine whether this center and that molecule are R or S. So the first thing that we do is we have to prioritize these groups. And so we look at the atomic number. So chlorine is going to have the highest atomic number of the 4 groups attached to that carbon. So chlorine is highest in priority. And then you know that the CH is going to have the lowest in priority. And what about these 2? This one has carbon directly attached to that chiral carbon, and this one has carbon directly attached to that chiral carbon. So here they tie, and so what you do is you look at what's attached to this carbon. So here you have 3 hydrogens, and here you have a carbon and 2 hydrogens. So this one is higher in priority. So in priority, you have chlorine is highest, this ethyl group is next, the methyl group is next, and the CH bond is lowest. And so what we do, the traditional way of drawing this is to put the CH bond going back away from you. So these 3 groups then are coming out at you. And then you go around this chiral carbon, going from highest to next to lowest of these three. So you'll see we're going in a clockwise direction. Cl, ethyl, methyl, chloro, ethyl, methyl. You have to go in a clockwise direction. And so if you move clockwise, that's R. If you move counterclockwise, that's S. So this chiral center has an R configuration. That means that this one is S. Okay? So we just went over. So you use the atomic numbers and prioritize the 4 groups. You arrange the molecule in space so that the lowest priority group, that's hydrogen in this case, faces away from you, which it was. You count the group priorities. So, and we did, we had chloro at the top, then ethyl, then methyl. We saw that that took us going from one to the other. It took us in a clockwise direction. Clockwise equals R. Okay, so that's the way that this is named. So the R is a prefix, and it will be in italics and in parentheses and followed by a dash as a prefix to the name. So this one will be parentheses R, close parentheses, dash, 2-chlorobutane. Okay? So let's use it again. Here, this is an ether. So here we have the, this is going to be a chloroethoxy propane. So here we have the 4 different groups. Chlorine is going to be 1 because it has the highest atomic number. Oxygen will be next. Then comes carbon. Then comes hydrogen. Now, a little trick to doing this rapidly, instead of redrawing this so that hydrogen is going back, if we determine, look at this, if we determine that this is going chlorine, oxygen, carbon, chlorine, oxygen, carbon, and that is clockwise, then when you flip the molecule over, it will be counterclockwise, going from those, going in those, in that direction. So this is actually going to be S. And you might want to go over that a few times to convince yourself that if you look at the designation, is this going clockwise or counterclockwise when hydrogen is coming out at you, which is not what you want. But in order to avoid rewriting the whole molecule, and sometimes it can be a large molecule, you go ahead and say, well, this is going clockwise, and so I'll just remember that, and then I'll flip the molecule over, and when I flip it over, it will also flip the arrow over, and the arrow will be counterclockwise, and so it will be S. And that's a shorthand way to remember that. And if that what I just said confuses you, then just ignore it and redraw the molecule and and work through the redrawn molecule with the CH bond pointing away from you, because that's the first thing that you're supposed to do, is point the CH bond away from you. And I've noticed in your textbook that the vast majority of drawings, they have positioned the CH bond coming out at you, which is not what you want. You want the CH bond going back away from you. And so you'll have to either just learn this or redraw everything. So now here, here he has redrawn this, he's rotated it, and he's redrawn it. And so now with the, this was CH here, with that going back, now you have, yes, so CH is going back here, the 4 is going back. Now you go 1, 2, 3, and you can see that that's counterclockwise. So this is a demonstration of what I just said. If it is clockwise with the CH pointing out at you, it's going to be counterclockwise with the CH bond going back. So if this is an yeah, so that's enough, I think, about that. And you'll just have to practice. Do some homework problems, look at your molecules, your molecular models, etc. Okay, so this is, I just did this. This is a repeat of what I just said. So this is counterclockwise, this is S, this is what we started out with before it was rotated. I just worked through that. I don't need to work through it again. So let's look at something that's a little bit more complicated. So here is a molecule that's a little bit larger, okay? And notice that you have CH2, CH2, and so you know that this nomenclature, assigning the configuration of this chiral carbon is going to be a little bit more involved. And so once again, as I pointed out, in your textbook, they have drawn the CH bonds coming out at you. And so that little trick I told you about, go ahead and analyze it with the CH bond coming out at you, and then just remember that in order to do it properly, you have to flip the molecule over, and so that will convert R to S, or clockwise to counterclockwise. So let's go ahead and do this. Now here, you know that the CH bond has lowest priority, and you know that the CO bond has highest priority of these four groups. When you look at this, this is carbon, and that's carbon, so it's a tie. And so you have to look at what's bonded to those carbons. And each of these carbons has hydrogen attached to it, and a carbon attached to it. So this one is carbon, hydrogen, hydrogen, carbon, hydrogen, hydrogen. So that's why it's saying this is a tie, okay? So we've got the highest priority and the lowest priority identified, but we don't have the ones in second and third place. So this is a tie initially, so you have to move out another bond. So now we're comparing this carbon to that carbon. And so this carbon is attached to two carbons and a hydrogen, which is not shown. Carbon, carbon, hydrogen, which is not shown. This carbon is attached to a carbon and two hydrogens, which are not shown. So that's why it says CHH. And so this one is going to be higher in priority because it's attached to two carbons, higher than this one, which is attached to only one carbon. So this group is second highest in priority, and this group is third highest in priority. So I hope that that explained that pretty clearly. So this is going to be 1, 2, 3. 1, 2, 3. And so that's going counterclockwise. If you flip this over, then that carbon will have an R configuration because it's counterclockwise while the CH bond is pointing out at you. When you flip it over, it will be clockwise. So another example. So notice that this molecule does not have a CH bond. So now we have to designate which is the lowest priority group. And so we look at the four groups attached to this carbon, And so here you have carbon, 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 carbon. All four are carbon. So you have to look at what's bonded to each of those carbons. Well, this carbon is bonded to an oxygen. So this is going to be highest in priority. This carbon is, and that carbon are each bonded to another carbon atom. This carbon is bonded, this methyl is CH3. It's not bonded to any other carbon atom. So this is going to be lowest in priority. So we're going to have to spend a little bit more time looking at these two groups. So this carbon is bonded to a carbon. This one is bonded to a carbon. So we have to move on out. This carbon is bonded to 3 CH bonds. This carbon is bonded to a carbon and 2 CH bonds. So this 1, 2, 3 butyl group is higher in priority than this ethyl group. And so we've got 1, 2, 3, 4. That's the designation, the prioritization, rather, using the Kahn-Ingold-Prelog rule. So if we look at this, this one is going to be highest in priority. That one is going to be next. This one will be next. And so we would be going clockwise. However, our lowest priority group is coming out at us. If you flip that over so that the lowest priority group is going back, then it would also flip this clockwise progression into counterclockwise. So this would be S. And the point here that we didn't even have to use, because this carbon is bonded to two oxygens, and we don't have any other comparison where carbon is bonded to just one oxygen. This is that this, when you have a double bond O or a double bond anything, it's counted as 2 bonds to that atom. Okay. This is another trick. Instead of actually rotating the molecule in your mind, you can swap 2 of the groups twice. So here, what is demonstrated is that 4 and 3 have been exchanged, and then 1 and 2 are exchanged. So this molecule and that molecule are the same. So you might try working through that. This molecule is not the same as this. This molecule is the same as the one at the end, because here only 1 pair have been exchanged, and you have to have 2 pairs exchanged in order to have the same molecule. So you should ignore this middle structure. R and S in IUPAC nomenclature. So, as I mentioned earlier, so this is R2-butanol. Look at this. You have the CH bond going back, the CH bond going back, and we have, this is the highest priority, this is next, so we're going clockwise. So this is going to be, this carbon will have an R configuration. The molecule will be the R isomer, and so it precedes the name of the molecule, this italicized capital R in parentheses followed by a dash. This is R2-butanol. It's 2-butanol because the hydroxyl group is coming at the 2 carbon. 1, 2, 3, 4 at the 2 carbon. Okay? And this is its mirror image, so it is S. Now here, what if we have a molecule that has 2 chiral carbons? So this molecule is going to be a 2-pentanol, 1, 2, 3, 4, 5 pentanol with the alcohol functionality at the 2 position. It also has a methyl group at the 3 position. So it is 3-methyl 2-pentanol. Okay? We number it so that the alcohol functionality has the lower number. And so we look at this, the OH group, the hydrogen is going back, and so the order of precedence of priority is 1, 2, 3. So that is clockwise. So this is going to have the R configuration. And so that says 2R because it designates that whatever it is in the 2 position is R configuration. This happens to be an alcohol, which we would know from that, but you don't have to put that out here. You just say whatever's in the 2 position, the chiral carbon at 2 position is R. Okay, and here it's saying that the chiral carbon at the 3 position, that's this one, which bears the methyl, it's saying that is S. And we can work through that. Remember that this has a hydrogen, which is coming out at you right now. So if we determine this with the hydrogen coming out at you, we would say that's highest in priority, that's next, and that is going clockwise. And when you flip this over to put the hydrogen going back, it would be counterclockwise, so that's S. So this is 2R, 3S. That takes care of both those chiral carbons, and they are in parentheses, all italicized, followed by a hyphen. Okay? So now, for the optical activity, which we're going to cover in just a minute, this is given because the carbones are probably the most famous pair of enantiomers. This is a common name. You do not need to remember or memorize this, but they're just very interesting, and so they're discussed to point out that these mirror images, see, this group is going out at you, and here it's going back, and so otherwise they're the same, and so these are 2 mirror images. This one is R, and that one is S, and they have the same melting point, boiling point, same vapor pressure, same everything, except the optical activity will be there, how they interact with other chiral compounds, or there's one characteristic of this pair which is very rare. There are a few pairs of enantiomers that we, humans, can detect. We can distinguish between these 2. These can be distinguished by their odor. This one smells like spearmint, and that one smells like caraway seeds. Spearmint and caraway. And normally when I have the class in person, I actually pass around a couple of bottles, a bottle of this and a bottle of that, and let students smell the difference. And 97% of the population can differentiate between those 2. They're the most famous. There are some others that can be distinguished by fragrance, some that can be distinguished by taste. And I've tasted them because I just wanted to, but I have never given those to students to let them taste. So that is our introduction into stereoisomers. And in the next class, the next lecture, we will look at more about optical activity and how to distinguish these 2, what it means for them to be optically active. And so this class is going to end